Hello everybody, my name is Archit Kamath. I'll be handling control systems for you. So this lecture is to basically tell you the path that I will take in teaching you control. Mind you, this is not the actual syllabus of control that you'll usually learn. Okay, like for example, the usual syllabus, you will have mathematical modeling as the first stage. Okay, but the thing is that mathematical model is not very frequently asked when it comes to GATE or ESE. Okay, so we look at those type of problems a little later on, but since our focus is basically to target GATE related problems, so the course that I am going to teach, the manner in which I am going to teach will be particularly targeted towards these competitive exams. One. Second, what I am going to do in this video is to give you a brief idea as to how my teaching can help you score a better rank in terms of GATE when it comes to controls. Okay, see, because what happens, controls is a very easy scoring subject. Alright, but the problem is that if you have a little bit of confusion also, you will tend to make a mistake and the entire thing will go. Alright, so the task at hand is to not only teach you control concepts, but also to teach you in a manner that you will absolutely have no confusions. And you know what's the best part about doubts? Doubts occur when you are sitting in the exam hall. They will never occur before that or anytime during the phase of your preparation. They'll exactly occur when you are sitting in front of the PC and writing the exam. Alright, such doubts are very dangerous and they should not occur. Alright, so the motive as to why I am teaching control in this particular manner, this strategy that I'm going to apply and teach you control over here, is so that you don't encounter such a problem. Alright. But for that, equal amount of cooperation is needed from you people side. So what should happen is that I am not going to tell you to note something down or please write this down and all of it, because you are all engineering graduates who are either pursuing or passed out engineers, you people are. So you are grown up enough to make your own decisions. So you know very well as to what is important, what should be noted down, what should not be noted down. It's up to you. But what is important is you should note down, and at least, if not for anything, what is compulsory to for attending my control system courses. Of course, I can't come to your home and stop you from doing it, but my sincere request to you all is that when I'm solving problems, please simultaneously note down the problem, pause the video. Alright, do not directly get into the solution, pause the video, note down the question, please solve it and then try to play it. There is no problem if you want to continuously see the solution and then solve it, no problem, but try and make an attempt, because if you will not solve problems now, directly in the exam hall you will not be able to solve. Okay, and all of this I am telling out of what experience. I will tell you, I have not written GATE 20 years back or 30 years back. I am a very recent person who has passed out of GATE, because of which I am telling you that GATE questions are not difficult. It is just that they'll ask you such basic questions that you will not be able to apply it then and there. It is not directly formula based. You will have to think a little bit, and what should be thought, it is my responsibility to tell you. Alright, so without wasting further time, let us directly get into the syllabus that I am going to follow. This is not the actual control system syllabus. Again, the syllabus I am going to follow that will help you target all the concepts of GATE in one go. Alright, so first thing that what we have to do is, because there are a lot of terminologies that you use in control systems, people tend to get confused with these terminologies, and questions, theoretical questions come on these terminologies. It is necessary for me to introduce these terminologies to you. One. Second, some tools are used, such as Laplace transforms, as all of you already know that Laplace transforms are used, but people don't know why Laplace is used, why not Fourier. So all of those things have to be answered. Third, some properties of Laplace should be learnt. And fourth, some terminologies related to some types of inputs, what type of inputs you have to give so that you can assess the performance of a control system, even that should be known. Alright, so all of this can be taught throughout the course of the syllabus, but it will just be too tedious, alright, to do it. So instead, what I have done is I have clubbed all of this under one topic heading, and that topic heading is called as basics of control system, which will be the first part that I'll be handling to you. Alright, so that is the first thing that I'll be, so let me just write down the syllabus here. So let's just do this. So syllabus. Alright, so first thing I will be doing is basics. Alright, so basics of controls, as I told you, will have all the tools and so on and so forth. Right, followed by this, The next thing, ideally what should have happened is, instead of basics, in your regular control system course, you have mathematical modeling. Assuming that you have already done mathematical modeling, the next stage is that you have a lot of interconnected systems. Alright, you have a massive interconnection. Physical systems are a connection of many subsystems, right? You all know that. Now the task is, I don't want so many subsystems because it becomes difficult to analyze. So I want to, what should I do? I should be able to merge all of these systems into one system, so that I will have one single input, one system, one output, so that it's very simple, very crisp. Rest of the analysis can follow after that, right? So the next stage of control system syllabus in actual and even for the gate, that is very essential, is block diagram reduction and signal flow graphs using Mason's formula. So that is the next concept that I will be handling. So let me just write that as BDR, block diagram reduction, and signal flow graphs, SFGs. Alright, so every year there will be at least one question from either of these topics, which is very essential, very easy to score. Alright, provided you are able to identify some parameters that are, such as loops and all of those, which I will tell you definitely as I am handling it, but very easy to score. Alright, after you have found out a consolidated system, you have transfer function, you have an input, you have an output, you know everything now. What should you do? You should be in a position to characterize some features about a system. Like for example, if you have a system that is of first order, just by looking at the system and saying that it's a first order system, you should be able to tell each time using Laplace and deriving the output is not a good idea. If you have some standard first order system, you know the output, then you know its behavior very easily, right? So on a similar lines, you have some standard second order system, you know the behavior. All right, so all of these should be done, okay, and these will be done in some a type of analysis called as time domain analysis. All right, so the next topic after this will be time domain analysis. Okay, in time domain analysis, what we are trying to do, we are trying to analyze for a time varying signal. All right, there is a time varying signal that is fed to a system, how the system will behave, what will be its transient response, what will be its steady state response. All right, when I talk about transient and steady state responses, you will understand that how important it is at the later stage when you learn to develop controllers and compositors, how important this particular analysis was. All right, so under this you have standard first order system analysis, standard second order system analysis, and one may question why aren't there other higher order systems as well. The reason for that is, if you have first and second order, putting them in cascade can give you all higher order systems. Alright, so what you do, if you have a third order, just split it into a first order and a second order, analyze both separately, and because they are LTI systems, you can simply merge the outputs and understand what's the behavior of the higher order system, right? But the problem is that always doing this, say it is 4th or 5th, okay fine, still you will be able to manage it. But if you have a 10th order or a 12th order system which is actually practical, like for example, if you have an unmanned aerial vehicle which is a 12th order system, suppose if you were to linearize that, you will have a s power 12 term in it. It is not easy to analyze such systems. Alright, when it comes to that, you will have to use some other type of tools. You will have to slightly think outside the box. Alright, since control system is a part of mathematics, everything in engineering is a part of mathematics, and so is control systems as well. There is a famous logic given by Routh and Hurwitz, which is used to analyze the location of the roots of a equation, okay, algebraic equation. All right, it was only for algebraic equations, but we adopted that in control and we now call it as Routh-Hurwitz criteria that you all learn. All right, so in this, apart from first and second order system properties, I am not writing that because by default that comes in here. What is explicitly important to be noted over here is the Routh-Hurwitz criteria. Routh-Hurwitz criteria. Alright, Routh-Hurwitz criteria, once again, mathematical concept, but since our characteristic equations are algebraic polynomials, we will use this concept and try to find out location of the poles. And by knowing the location of the poles, you will be able to tell whether a system is stable or unstable. And where will you get this knowledge? You will get this knowledge from the basics lecture. Because in the basic lecture only I would have told you that in which direction the pole should be there in the S-plane to judge whether a system is stable or unstable. Right? So this particular thing is very important, after which all of this becomes very easy. Alright. After Routh-Hurwitz criteria is a table. Okay, since most of you know, there is no graphical representation. But if you want a graphical representation, if there is a parameter in the transfer function that you are varying and you want to see how the poles are moving, alright, as that particular parameter is varied, graphically, you have another tool called as root locus diagram. Alright, so root locus diagram is the next most essential. Root locus diagram or root locus plot, whatever you want to call it, that is the most essential thing. And let me tell you one thing as to why root locus plot is thought after Rao-Hurwitz criteria. Many people ask it, can this be thought interchangeably? But no, you can't do that. Why you can't do that? Because there is a parameter, okay, there are parts in the root locus plot that can be found out only by applying Rao-Hurwitz criteria. And what is that? The critical value of k at which the root locus plot will cut the j omega axis, right? So that thing can be only analyzed using Rao-Hurwitz criteria. Alright, after this, these are basically meant for transient responses. Alright, transient response you can find out, or the transfer function characteristics you can find out by doing so far time domain analysis, Rao-Hurwitz criteria and root locus plots. After this, you have a steady state also. After the transient is done, you will have a steady state. Now in the steady state, you want to see whether there is an error between the output that the system is giving and the actual output that you wanted the system to do. Alright, there again in that particular portion, I want to, though it is a part of TDA, that is a time domain analysis, I will explicitly write that as error analysis. As to why I am writing this explicitly is, there are a lot of confusions that people get into at this stage. Every year GATE asks one or the other question directly or indirectly related to this. People still commit a mistake. Despite every year the similar concept being asked, people commit mistake. It's not because they are negligent, it's because genuinely at some stages they have a doubt which they will not realize when actually sitting in the class and when the professor is teaching, because he himself will not address that. So my task here is to make you understand error analysis in a manner that you will absolutely not have any confusion. Even if you try to have a confusion, automatically your logical reasoning will negate that. Okay, and why I am telling you this again and again is because the doubts will always arise in the exam hall, and negating it then and there is what is important. Alright, so error analysis. After we have performed error analysis, time domain is done. Now time varying inputs are done. There is something called as frequency varying inputs. As the frequency is changed, how the system is behaving. To do that, we have another domain called as frequency domain analysis. Alright, in frequency domain analysis, just like how you have tools like root locus plots over here, you have some type of criteria even here, right? So you have polar plots, Nyquist stability criteria. So just let me write this as Nyquist stability criteria. Alright, why didn't I write polar plot again? I will tell you over here, because polar plots are not very commonly asked. Okay, what they do ask you is Nyquist stability criteria, which everybody have a lot of confusion in, but it's actually very easy. Some shortcuts will be told to you during my lecture, which will help you able to tackle all type of problems in that. Okay, after Nyquist stability criteria, then you have Bode plots. Bode plots. Alright, frequency domain plot, Bode plots are there, which is very easy to score. Okay, no confusion arises over here. It's very easy to score. People make mistake in calculating slope. The things that you learn in 7th standard, people commit mistake over here because it is not their fault again. It is because the unit of the slope is a little different. It is not in centimeters or meters, or rather the axes are not in centimeters. It's in frequency, and you have per decade. Alright, dB per decade. The moment dB per decade comes and logarithm comes, people commit mistake. Alright, so how to remember that? How to make it more easy? How to make it as simple as calculating the slope in coordinate geometry? That is my responsibility. It's my guarantee to you at the end of my lecture, in that you'll be able to just look at the transfer function and randomly draw the Bode plot with all the slopes right. Alright, so that is an essential portion of the frequency domain analysis. Now, one very important question is, if by chance, okay, just a tip, side note at this stage is, if you did not use Laplace transform and you try to analyze whole of control system with using only Fourier transform, this entire portion of time domain analysis and error analysis would have got completely eliminated. Alright, only frequency domain analysis you would be able to do. Alright, as to why it is like that, that I will tell you in which lecture? In my basics lecture. So basics lecture is very, very important. Without looking at the basics lecture, please do not attend any other class. It's absolutely useless. Alright. So after this, the next concept, you have done time domain analysis, you did frequency domain analysis. Now you have understood the system completely. Alright. Now you know what is missing in the system. Okay, you know what should be compensated, you know what behavior should be controlled. So the next topic is controllers and compensators, which is very, very easy to score, but people are very fearful, because of which they do not attempt the question itself. And all the IITs who set your paper know that as well, because of which they give you a lot of comprehension type questions in this stage, right? So they will give you 4-mark questions in controllers and compensators, which very easy 4 marks you could have got, but because you have not done it and lot of confusion or anything is there or some fear is there, you leave it. All right. So it is my responsibility to simplify that. All right. So controllers and compensators will be taken over here. Okay, C and comp. All right. Short forms, but you people please make full forms in your thing. After this, the last topic, okay, is completely related to linear algebra. Actually, a math professor can teach it much similar to what a control professor can teach. Okay, it's actually not control, but we have adopted the mathematical linear algebra concept completely into control, and we are trying to make sense of the mathematical results in our control, and that particular domain is called as state space analysis. Okay, state space analysis. All right. Here you have concepts of state transmission matrix. You have something called as observability, controllability. Every year it is asked, what is observability? What is controllability? Basically, what are those? Basically, what is happening when you create a matrix, if the rank is less than the order, some of the properties get covered. Like for example, something that should have been visible is not visible. The moment something that was should have been visible is not visible, you say it is not observable, right? It's a mathematical concept, but we are using it here trying to make sense and trying to analyze control systems. All right. So how to do that? How to remember it? How to just look at the matrix and understand whether a system is controllable or observable? All of those which will be asked very frequently in GATE, all of that I will handle over here. Is that the end of the syllabus? Actually, no. There are 2 more other concepts which will be handled, but which are very, very special and unique. One, mathematical modeling. Okay. Electrical systems, mechanical systems, very commonly asked. Why I am going to do those is not only for the GATE perspective, and this will be handled at the last, because not only for GATE perspective, because you all should, before writing GATE and getting into IITs for MTech, you have to pass your BTech degrees also. By failing BTech, you cannot do your masters. So to pass your BTech degree, you have to write control systems in your board and in your whatever university exams. Their block diagram is definitely asked, rather mathematical modeling is definitely asked. So I will teach you that. Okay, electrical and mechanical systems, it's my responsibility, I'll handle that. Second, in ESE, they ask a lot of question on sensitivity. Okay, and none of the institutes and all handle sensitivity very seriously. All right. So sensitivity will be a separate lecture with very good problems which have been asked. How they affect feedback, a detailed video will be made, but it will be done at the last, because people should understand all of these concepts to understand the sensitivity in depth. What happens? Sensitivity is that chapter that is usually placed here just after basics. Actually, you can consider it as a part of basics, but the problem is that covering it there will be like, I don't know, teaching a person to fly a plane theoretically and then directly putting him in the cockpit and saying, okay, now fly it. All right. So it's of no use. Okay. Teaching you that knowledge over there is absolutely useless. Okay. We will handle that at the end. All right. So my logic is like this. When I'm handling all of these concepts, unlike any other subjects which I don't want to name, these subject cannot be a theoretical class. Okay, I will be solving problems and telling you all the concepts. So definitely you will have a lot of problem solving during the lecture itself. In addition to that, I will be handling at the end of the lecture, end of all of these lectures, explicitly miscellaneous collection of problems, around 70 problems there. All right, I will be handling almost 70 while solving this also. All right, possibly. I am not sure about the number. It may exceed, it may be less, depends. But I will try to cover umpty number of problems. In addition to that, you will be given practice sets also, as Professor Rao has committed. All right. So with that, your control systems syllabus will be completely covered, and there will be some doubts such as, will those problems be enough? Because many of them have asked me this, so let me cover this in the introductory video and only close this topic. Will these set of problems be enough? All right. See, people who ask this question are those people who learn 20 problems and the 21st problem they are not able to solve. Okay. Do not be that kind. If you are being that kind who is able to solve 20 problems and who is not able to solve the 21st one without using the knowledge from the first 20, then you are not fit for GATE. Okay. Don't take it in a negative sense. Be the other kind. Be the kind that who solves even 200 problems but should be able to extrapolate that knowledge in another manner. To do that, we have to meet both the ways. All right. You should also work hard, and we will also give you problems where every problem is different from the other. You will see that none of the two problems match, no matter what. All right. Why we are doing that is so that we give you as much flavor as possible. And once we give you so much flavor, you should be able to extrapolate from that knowledge any other problem that will come. And possibly, to the best of my ability, I will see to it that you may not require that situation where you will have to extrapolate in the exam hall. All right. We will see to it that you will only have to do interpolation, where with whatever knowledge you already have, you should be able to see the question and solve. All right. So with that guarantee and that promise, let us move on to the first most important lecture of control system, which will decide the future of the entire course, which is very necessary. All of you, please attend it under every condition. Do not miss this. All right. That is the basics to control systems. All right. So let me see you in that class. Thank you very much.